Great. Okay, so welcome everyone. This is the Recommender Systems workshop. My name is Jack. I've sent the slideshow and notebook into the chat. So these should be resources for you to look back on and kind of remind yourself of what we talked about in the workshop. The goal of them was kind of just to act as resources for you. So I just wanted to say at the beginning, you don't have to take notes. There's going to be quite a bit of content, but the whole goal is for you to build some intuition for how to build a recommender system and like the inner workings, how it works, and some design decisions you might have to make when you're working with your own recommender system data set. So let's begin. So first, just a quick introduction. My name is Jack Douglas. My pronouns are he, him. I'm in 2B software engineering. This is my email, just jack.douglas@uwaterloo. This is my LinkedIn. I can send this stuff into the chat at the end as well. Let's keep going. So here's just a general overview about the intended audience and the goals for this workshop. This workshop is open to all skill levels, and I want to note that I will be going into a little bit of math for those who are interested, but if you don't understand all the math or you haven't taken like linear algebra or you haven't taken multivariable calc, that's totally fine. I want to emphasize that because we will also be talking about how the recommender system works from a higher level and how they relate to machine learning concepts. So it's open to all skill levels. As well, you can take notes, as I said, but I recommend that you just sort of try to absorb the information, just keep engaged, and I'll ask periodically if anyone has questions. And the goals of the workshop are to learn about what recommender systems are and the types of data that you will see in the real world. We will be looking at two traditional recommender system approaches, content-based and collaborative-based filtering. And then we'll also learn how to implement a recommender system of your own. And we'll be using a movie ratings data set to illustrate this. So the outline for what we're actually going to be talking about, we're going to start by saying what is a recommender system. Then I'm going to give you the motivation, basically why you should care. Then I'm going to be talking about how recommender systems work and the types of data that you'll see when dealing with recommender systems. I'll go over some useful notation for describing data sets, and then we'll get into the main focus of approaches to recommendations, which is we're going to be looking at content-based and collaborative-based filtering. Those are the two traditional, most popular recommender systems. There are others, and I'll briefly touch on it at the end, but understanding content-based and collaborative-based is essential for your foundation to understanding recommender systems. So let's begin. What is a recommender system? Well, I've given a quick definition of what a recommender system is on the slide. It's basically a type of machine learning system that recommends new products and services to users. From a higher level, recommender systems look at how the past behavior of users can be used to recommend new products to them. And there are a number of different ways of coming up with these recommendations, and we'll be focusing on two of them later on. But as you can see in this funny image of Homer on the right, the general idea is that Homer has bought some Duff beer before, and our recommender system wants to come up with recommendations for new products that Homer might like. In this case, a Duff t-shirt. And the reason it's being recommended to him is because it's the same brand as the beer. This is just a comic to illustrate from a higher level what recommender systems do. But before we go on, you now have a very basic understanding of what a recommender system is. And now I want to tell you about why you should care about them and why you should stick around until the end of the workshop. So simply put, recommender systems are used everywhere. Every one of you here has used multiple recommender systems every day, whether you consciously realized it or not. Some examples of some everyday recommender systems that work include your Instagram feed, advertisements and search results in Google, song recommendations on Spotify, movie recommendations on Netflix, and many more. All businesses are interested in recommender systems, whether directly or indirectly, because they want their products to be recommended to potential customers. And the better the recommendations, the more likely people are of buying their product. So this makes both the customer And business is happy because users are being recommended things that they actually want and not things that they don't care about. And it makes businesses happy because it makes them more money. So having good recommendations is clearly important. But despite their important business applications, uh, many programmers who are new to ML often overlook learning about recommender systems. And as well, if you go to a machine learning conference, you likely won't see any presentations about recommender systems. However, if you ask many of the companies who are sponsoring those conferences, many of them will talk about how they look for understanding of recommender systems as one desirable skill in potential hires. So there clearly is a demand for developers who can create good recommender systems for many of these big tech companies shown on the slide. And if you stick around until the end of this workshop, you will hopefully be able to implement a recommender system on your own and display your knowledge of recommender systems to help your resume stand out. Okay, so let's get into how a recommender system actually works. Well, recommender systems seek to understand three key relationships: the user to product, the product to product, and the user to user relationships. I've provided a basic explanation of what each relationship refers to, and they are fairly self-explanatory, but still important to be aware of. Um, Throughout this workshop, I will frequently be using movie recommendations as a running example because it is easy to understand a movie recommendations notebook, or sorry, movie recommendation data set. So I'll just go over some examples of each of these relationships while using movies as our example. But before I do that, I also wanted to note that a combination of these relationships is what's used to basically sort the best recommendation for users. And I also wanted to point out that although I'll be using movies as a frequent example, you can generalize this to any sort of product, whether it's restaurants or books or any sort of product that is recommended. So if you're on Google Maps, when you search like food near me, Google is using a recommender system based on different ratings of the different restaurants around you and how people have liked and disliked them. If you say like near me Thai food or something, it'll do the same thing specifically for Thai food, etc. So let's move on. So an example of the user to product relationship is we have here is that user one has rated the movie Step Brothers 5 stars out of 5. So from a higher level, we want our recommender to capture information about this rating. So a simplification of this would be for our recommender system to have a profile for user one, and it basically increases user one's preference scores for different attributes of the movie. So Step Brothers is a comedy. It stars Will Ferrell and John C. Reilly. So the preference scores for all three of those comedy, Will Ferrell and John C. Reilly, should basically be improved or increased. Again, this is a higher level. We'll talk a bit more about how this actually looks like in a data set and how this actually looks like when we're representing a user's preferences, basically. Okay, the second type of relationship, product to product. So here's an example where we have Goodfellas is a similar movie to Taxi Driver because they have similar casts, similar genres, they have the same director. So we want our recommender system to capture that information so that if a user enjoys Goodfellas, that depending on our approach for our recommender system, that we can give this user recommendations such as Taxi Driver because they enjoyed it. And then the last relationship is user to user. Again, fairly self-explanatory. We have two users that are similar, and they both like. They're similar because they both liked Iron Man. They both gave it 5 stars out of 5 stars. So we want our recommender system to capture that information so that if user one then goes out and likes another movie that user two hasn't seen, then we can recommend that movie to user two. Okay, moving on to the types of data. So there are 3 types of data. The first type of data is user behavior data, and it comes in the form of explicit ratings and implicit ratings. Explicit ratings refers to ratings provided by the user. So some examples of that are ratings like our movie examples. They can be reviews, likes, following, and many more. Implicit ratings refers to ratings provided from users interacting with the product. So some examples of that are clicks, views, purchases. And basically, user behavior data is the most important type of data because it's used in every type of recommender system. So you always need some form of, whether it's explicit or implicit rating from users. And on the right is an example of explicit ratings for 5 movies: Step Brothers, Anchorman, The Other Guys, Taxi Driver, Goodfellas. And we have 2 users, user 1 and user 2, and they've given ratings for each of these movies from 1 to 5. And where there's a question mark, that means that they haven't rated that movie quite yet. So our goal is to basically recommend new movies to user 1 and user 2 that they haven't seen. So like where there's a question mark. And we want to recommend movies to them that we think they would like. So that's basically how we would use this data. The second type of data that people use in recommender systems is user demographic data. This is pretty self-explanatory. Some examples of it are age, location, and income. And they're really just used in recommender systems to help improve the recommendations. So they're not necessary, unlike user behavior data, which is necessary. This can just help improve our recommendations. And an example of this is if someone searched phone charger and our recommender system knew that they were located in North America, then the result would be a North American adapter. Whereas if someone in the UK searched for a phone charge adapter and a recommender system knew that the person searching was in the UK, they would give the UK adapter. So again, pretty self-explanatory. The last type of data is product attributes. And this is a pretty clear example where some examples are genre, type of item, the company producing the item. So it's just all sorts of information about the product. And so on the right, we have a Nike t-shirt, and some example attributes are that it's Nike, the brand, it's a t-shirt, it's black, it has a graphic, and you can collect many other more specific attributes, and this can help to improve the recommendations. Product attributes are necessary for content-based filtering, but they're not necessary for collaborative-based filtering. I'll explain what those two mean later, but and I'll jog your memory when we get there about the types of data that we need for each, but let's move on. So here's an example of a movie rating data set. It's a data set with explicit ratings and product attributes. So as we can see, we have the 5 movies that I referenced before. We have 2 users, but then we also have information about the types of genre. Those are the product attributes. So we can see that Step Brothers is a comedy, but it's not a drama. Anchorman is a comedy, it's not a drama. The Other Guys, comedy, not a drama. But then Taxi Driver and Goodfellas are comedies, are not comedies, and they are both dramas. So let's move on. So here we have some useful notation. You don't have to memorize this or something. It's just a useful way of describing basically this previous data set that we saw. And it's a useful way for understanding some of the math that we're going to be using later on. But I've given some examples here for the notation. So we have our data set on the top left and our notation on the right. So our first piece of notation is to check to see if user J has rated movie I. And we denote this R of IJ. And if the answer is 1, then that means user J has rated movie I, and it's 0 otherwise. So our first example is whether user 1 has rated movie 1. And if we look at user 1 and we look at movie 1, that's Step Brothers, we see that user 1 has rated Step Brothers a 5. So therefore, user J has rated movie I, or user 1 has rated movie 1, sorry. And so that means that we give it a 1. The second example we have is we want to see if user 2 has rated movie 4. If we go down the column user 2 and we look at movie ID 4, that's Taxi Driver, we see that there's a question mark. So we know that user 2 hasn't rated movie 4, and so we give that value a 0. The second piece of notation is the feature vector, and this is an important part of notation. So is the parameter vector, which I'll talk about in a second. But basically, the feature vector is a vector that tries to represent each product in terms of the attributes. It's important to note that the first index is always 1, and then each subsequent index after the first index refers to the attributes. So in this case, if we look at the feature vector for movie 2, which is Anchorman, our first index is 1. And if we scroll across, we see that x1 is 1 and x2 is 0. So our following two entries in our feature vector for movie 2 is 1, 0. So collectively, the feature vector for movie 2 is 1, 1, 0. And then we have an example for the parameter vector for user 1. This basically, I won't go into details, super close details about how we came up with 505, but essentially we want to represent the likes and dislikes of user 1 across all the movies they've seen. So if you look at the user 1 column, you'll notice that he or she likes, or user 1 likes funny movies. So we have a 5 at the top. We don't really know about whether, user 1 likes Step Brothers. We don't really know if user 1 likes Anchorman or the other guys, so we've given that a 0. And we know that user 1 likes Taxi Driver and Goodfellas. This is kind of a simplification, and we'll actually go into more detail later about how we find out exactly what the parameter vector is. But for the time being, I just wanted to give you an example of what a parameter vector for a user could look like. And then finally, I have some examples for the notation for what an actual rating is. So y of 1, 1, we look at user 1 and movie 1. We see that user 1 gave movie 1 a rating of 5. And for the second example we have is what did user 2 give for movie 1? If we look in the data set, we see that user 2 gave Step Brothers a rating of 1. And then our last example is looking at what user 1 gave movie 2, we see that they didn't have a rating, so the value is undefined. The one piece of notation that I didn't give was basically the last line, which is predicted ratings. That's essentially how our recommendations are formed, and I'll talk about that a bit more later. But it's essentially using some of the notation that we've previously defined. We're taking the inner product of the parameter or user vector. They're sometimes called, the parameter vector is sometimes called the user vector. But we're taking, essentially what's happening is we're taking the inner product of the parameter vector and the feature vector, and that actually gives us the predicted rating by user J on movie I. And so this is using some linear algebra. So if you haven't learned linear algebra, that's okay. It will make a bit more sense when I give a higher level explanation a bit later. Okay, so now we're at approaches to recommendations. So there are, we're going to be talking about content-based, collaborative, and hybrid is actually a mixture of the two. And we'll see that most commonly hybrid is used because the advantages of content-based are actually solve some of the disadvantages of collaborative and vice versa. But quickly, I've listed some definitions for each. Content-based is essentially when we recommend products that are similar products to what a user has liked in the past. So in the graphic on the right, we see that a user has read a whole bunch of documents. We then find documents similar to the ones that they've previously used, and then we recommend those to the user. Collaborative based recommendations are created by finding finding similar users and then recommending products to each user that one has seen and the other hasn't. So in the graphic on the right, we see that we have two similar users since they've both read the same documents. But we have some documents that were read by the person on the left, and we recommend those documents to the person on the right. Okay, so let's go into depth first into content-based filtering. So I've just repeated the definition here, but just to remind you of what it is. But what's going on here in this approach is that we're actually using the user to product and the product to product relationship. So that's how all those slides that I was talking about earlier in the presentation about the types of relationships, that's where that information kind of circles back. So this approach is all about focusing on the user to product and then the product to product relationship and combining them. The types of data that are used with content-based filtering is the product attribute, and that's necessary because that's the only way we can understand the product to product relationship. And then we also need user behavior because, as we said, all types of recommender systems need user behavior, and user behavior refers to the user to product relationship. And so we need at least one rating before we can start giving recommendations. And so basically where machine learning ties into all of this is that we assume that we are given the feature vector. Our feature vectors are from the product attribute data, and we must learn the user or parameter vector using linear regression. So this might be, if you're not familiar with linear regression or machine learning, this might be daunting, but I'm going to give you a quick overview of what basically I'm talking about. So in machine learning, typically you use what's called a loss function, or a loss or a cost function, and an optimizer. And basically, our goal within machine learning is to model data in such a way that we can extract insights about the data. So if we have a model, if we wanted to create a model that predicts the price of houses based on the size, the square footage of the house, we might have a whole bunch of data that has this mapped, and then we want to be able to determine if a house of a specific square footage, what the price of that house will be. And so we can use linear regression and a loss function and optimizers basically to solve that problem. But I've listed some definitions for a cost function and an optimizer. I'll just read them out loud really quickly. So a cost function is a function which calculates the error in the model across all samples. So basically we start off with a very bad model, but we want to calculate just how bad it is and then make a slight improvement. And then we recalculate how bad this new model is, and then we improve it slightly more. And these improvements are basically made by using the optimizer, which aims to minimize how bad basically our model is, and it improves our model by changing the training parameters. So here's an example of a loss function. This is the mean squared error loss function. And basically what it's doing is you're taking the difference between the predicted value, the predicted output yi, and you subtract the actual value, which is y tilde, like yi tilde. We square that and we sum it across all the data points n, and then we take the average of that, and that's our mean squared error. So this is a common loss function. We'll actually be using this exact loss function later when I'm talking about our recommendations again. But this is how basically any sort of linear regression or classification problem is solved. You have to have a loss function, and then you also have to have the optimizer. So gradient descent is a very common optimizer that everyone should be aware of. And it's okay if you don't understand the math. I've given some diagrams to kind of illustrate what gradient descent is doing. And from a higher level, basically, you want to find the global minimum where we want to minimize the cost function, and gradient descent does that by slightly changing the parameters of our model to improve it, as I was talking about earlier. So gradient descent is an algorithm that basically does that. At the bottom is a formula for gradient descent. I won't get into too much detail, but for those that are interested, on the far right, the partial derivative is referring to the loss function, and alpha is the learning rate, which is a concept that, again, only for those who are interested in the specific parts of the math. If you haven't learned linear algebra or multivariable calculus and you don't understand it, that's okay. I would recommend, though, if you're really interested in machine learning, that you maybe take a course or just read about it online. If you've taken any form of calculus, multivariable honestly isn't very much harder, at least understanding the concepts that you need for understanding machine learning. But yeah, so I think I've given a really quick rundown on what some very large concepts in machine learning and linear regression. Basically, we have a model and we calculate how the model performs, and we want to make improvements to that model, and we measure it by using a loss function, and we have an algorithm which basically makes the proper changes to improve it on each iteration. Okay, so now we have the optimization with content-based filtering. And so the formula I have on the right, where we're minimizing over theta j, our parameter vector, and then we have our mean squared error. So we see it come back. So that is our cost function. And basically, as I said before, with content-based filtering, we are given the feature vectors, and we want to learn the user slash parameter vectors. So basically, we start off with some random values for theta j, and we take the inner product with our feature vector at I, and then we calculate the mean squared error, and then we use gradient descent to basically change theta j such that our mean squared error is minimized. So I've also provided the notation in the top right, where I've reminded you that theta j with in the inner product of theta j and xi gives us the predicted rating. So our goal is that our predicted rating is as close as possible to the actual rating, y of ij. So hopefully that gives you a higher level understanding of what's going on here. We're basically we know what x of I is, that's constant. We know what y of I of j is, that's also constant in this scenario. And we're wanting to figure out what values for theta j make that inner product equal to y of ij. And we do this for all users. We want to do this for all the user slash parameter vectors, and we're given all the feature vectors. So I've only shown the formula for theta j, but we really do this for theta 1 all the way up to the last user, like theta n. So yeah, that's how content-based filtering works at a technical level. And on the left is the type of data set that you'll see when you're wanting to do content-based filtering. A reminder that you have to have explicit ratings, you have to have some sort of user behavior ratings, and you also need product attributes. So if you ever have a data set where you want to make a recommender system, one indicator of using content-based filtering is if you have clear product attributes. So that can be an indicator that you'll want to use content-based filtering. Okay, so then on to the second approach to recommendations, collaborative filtering. So I've just listed the definition again to remind you. It's basically a way of recommending products to users that have liked similar products in the past. In this case, the collaborative filtering is using the user to product relationship and the user to user relationship. And so the types of data that you'll need for collaborative filtering is user behavior, as does all recommender systems. But you'll notice that's the only type of data that collaborative filtering needs. However, you need many ratings, or you need many records of user behavior, because you won't be able to find a good user-to-user relationship if there are too few ratings. So, for example, if you have a user that has only rated one product, you won't be able to find an accurate user-to-user comparison for that new user. So you assume that for collaborative filtering, you assume that you are given the user slash parameter vector, and we must learn the feature vectors because we don't have the product attributes, and we do this using linear regression. So very similar, but to content-based, but we're just seeing that we're given the opposite basically, and we're trying to learn the other vector. So in this case, we're given the user parameter vectors, we're given theta j, but we're trying to learn now the feature vectors. We're trying to learn x of I. So basically, same situation, we're using linear regression again, and we're using mean squared error as our cost function, and then we use gradient descent to improve our, when we're using gradient descent, that's where we're actually learning the feature vectors. So yeah, we can see that there's clearly two different situations where we use one or the other, and it's mainly dependent on the type of data that's available to us. So if, for example, you have a data set that doesn't have product attributes, that will be an indicator that you'll likely want to use collaborative filtering, because you don't have access to the product attributes, so you can't do content-based. So yeah, that's, and on the left, we can see our data set has explicit ratings and it doesn't have product attributes. So as I said, it's an indicator for why we'd want to use collaborative filtering. Okay, so with that all being said, let's just look at some of the advantages and disadvantages of these two approaches that I've presented. So the advantages of content-based is that, or the biggest advantage is that you don't need many ratings from users before the recommendations are usable. So we can somewhat avoid the cold start problem, which refers to when you have a new user who doesn't have many ratings. Even if they have just one rating, you can actually start to get usable ratings for that new user, which is a pretty big advantage. However, it also has a couple of big disadvantages, which is that new products are less likely to be recommended to users. So products won't get, many products won't get the same exposure as others. And that's because the recommendations that you'll receive are typically just based on things that you've previously liked. So I'll give an example of that. If I bought a baseball shirt or a baseball jersey, and a baseball bat and a baseball glove, I'll likely only get recommended other baseball items, but it's unlikely that I'll be recommended basketball items, for example, or soccer item like soccer cleats or basketball or other sorts of things, because the recommender doesn't know that I like that type of content. It only knows so far that I like baseball. So that's one disadvantage of content-based. The other disadvantage of content-based is that you just need more data. So lots of times in machine learning, data is the biggest limiting factor. And so the fact that you need product attributes to do content-based recommendations can sometimes be, it's often the determining factor between whether you use collaborative or content-based. Many times, if you really want to do content-based, you can go out and get people to collect that data, but it's just that that's an additional cost. And so sometimes that additional cost might not be worth it. So then people will just resort to collaborative based. And so I'll go over the advantages and disadvantages of collaborative based. So the first one for collaborative is that it's very easy to implement, as we'll see in the notebook that I'm about to go over. And you don't need product attributes or feature vectors. So as I said, you need less data, you need less different types of data. So that's a big advantage. However, there's also a couple of disadvantages, which is that user preferences change over time. So some of the things that you used to like may not apply. So the user to user relationship may not be accurate over long periods of time. And then the other big disadvantage is that you need many ratings from the user before recommendations are usable. So that's referring to the cold start problem, where a new user won't have a very good user-to-user, the recommender won't be able to have good user-to-user relationships. So the recommendations you get will not be very usable. So as you may have noticed, that was an advantage of content-based. The cold start problem was an advantage of content-based because it doesn't have that issue, but it was a disadvantage of collaborative. And similarly, disadvantage of content-based is that you need more data, and that was an advantage of collaborative-based. So that's why in practice, most people use the hybrid approach, which is where you actually use a combination of both, because as I've explained, the disadvantage of one is the advantage of the other, and vice versa for content-based versus collaborative. So in practice, most companies end up using a combination of both. Okay, so now let's go on to the notebook. Oh, shoot. Okay, so on issue, I'll just run it really quickly. But, oh wait, I guess the results are already here. So it's on issue. So is everyone able to access the notebook? I sent it at the beginning. If new people came, I'll just send it again. 1 sec into the chat. But just a reminder that you can make a copy of this by going to File, and then you just save a copy in your drive. That way you can edit it on your own. At the moment, I think you just have viewing privileges. So you're able to keep a copy of this and make the changes that you want and play around with the code I have here. The goal of this notebook is to implement a collaborative filtering recommender system and go over a bit of the processing for the feature vectors for content-based filtering. So I'm going to be doing the full implementation of collaborative and just part of the content-based. The reason for doing that is because, as I said in the advantages and disadvantages, collaborative filtering is much easier to implement, and there's a lot of libraries that make that super easy. But content-based filtering is a little bit more difficult, or it's more difficult. It's not, I wouldn't say it's hard. It's just that I didn't want to spend this entire notebook going over processing, processing and formatting techniques, especially when there's a usable recommender approach, collaborative filtering, which is much easier to implement. So long story short, if you are trying to work on your own recommender system, I'd recommend starting with collaborative filtering, and then you can maybe move to content-based filtering, and I'll give you some tips on how to get started for that, basically. So in this notebook, we'll be using the Movie Lens 100K dataset. Movie Lens has a bunch of data sets containing explicit ratings for thousands of movies from thousands of users, and there's data sets of varying sizes. I chose the smallest one just for resource limitations and stuff. So you can read more about Movie Lens at this link. As well, the big library that we'll be using for our implementation of collaborative filtering is the Surprise Scikit package. It's a fantastic package. You can read more about it at the link I've provided, but it makes implementing collaborative filtering recommender systems as easy as just a few lines, which is fantastic. So yeah, let's get into the actual code. So here I'm just installing the packages and libraries that we'll be using throughout the rest of the notebook. So I'm installing the Scikit Surprise package. I'm importing Pandas for data analysis and handling of our data frames. I'm importing NumPy and then I'm using the aliases PD, NPy. Those are just common aliases for these libraries in data science and machine learning. So basically, I just don't have to type out NumPy or Pandas every time whenever I'm using one of their methods. And NumPy is just used for computation and data analysis. It's a really useful tool in data science. So is Pandas. And if you aren't familiar with them, I'd highly recommend reading more about them. I think we actually have some previous workshops on both, so I'd recommend checking out our YouTube channel to learn more about them if you haven't. And then TQDM is just a progress bar library. It's not necessary. But then the big library that we're using, as I said before, is Surprise. So we're importing the dataset and reader modules for just handling our dataset and reading it in. SVD is the algorithm that we're going to be using. I'll explain a bit more about that when we get to that part of the code. And then I'm importing the cross-validate module as well to assess how our recommender system is doing. So let's continue. So as I said before, we're using the movie lens 100K data set for this notebook. It contains 100,000 ratings. It contains 3,600 tags, and they're applied to 9,000 movies that were rated by 600 users. So you can download this specific data set at the link I've provided, and you can find other recommender system data sets at this other link I've provided. I think it has a data set with book ratings. It has ones on jokes. So those would be maybe side projects that you might want to do on your own, or you can just search online for different recommender system data sets for some other particular, maybe it's a hobby or some other product that you're interested in getting recommendations for. But if you want some quick data sets, I've provided a link there. What I'm doing here is I'm just mounting my drive onto this notebook. What that's doing is that it allows me to have access to all my files in my Google Drive. And this is something you just do in Google Colab. You wouldn't do this in like a typical Jupyter notebook. It doesn't have that functionality, but that's one of the reasons I enjoy using Google Colab. Google Colab, by the way, is just this like notebook that I'm working in. It basically makes running Python scripts a lot easier, and I can include Markdown in them as well. So it's just a common tool that data scientists use. So just in case you guys didn't already know about it. So right here, I'm using Pandas to read in our SVV files, which are our data sets. We're reading in the movies.svv and the ratings.svv files. Note that if you wanted to run this exact notebook on your own, you must first download the dataset as I mentioned here, and then you must change the file path in your drive so that it points to where these files actually are in your drive. In my case, I have it like in a file path that goes into my UW folder, data science folder, this workshop, etc. So just make sure to change these pathways when you're running this on your own. So if we look at the first 5 entries of the movies data set, we'll see some examples of the types of data that exist in the movies data set. So we have the movie ID, titles, and we have genres for each movie that are separated by pipes. I'll talk about that a bit more when we get to the processing section. And then we also have our ratings data set, which has user ID, it has the movie ID, and it has the rating of the user, the rating that the user gave to that particular movie ID, and then it has a timestamp for when that rating was given. So what I'm doing right here is I'm just using some tools in Pandas for restructuring how the data actually looks like. It's the same data set, I'm just revisualizing it. And by doing that, we're actually able to get a data set that looks very similar to the data sets that we had in our slides. If you remember, in our slides, we had a whole bunch of movies with IDs 1, 2, 3, 4, 5, just like this. In reality, though, I just want to point out that head is only showing the first 5 entries. So there's actually, this data set is much larger than just 5 rows. But just by head, if I did like head 30, it would show the first 30 rows. Anyways, but then at the top, we have the user IDs, just like we did in our data set example in our slides. So as we can see, user 1 gave movie 1 a rating of 4.0. And everywhere where it says nan, that just says not a number, which basically means that no rating exists. So user 1 hasn't rated movie 2, but they've rated movie 1 and movie 3, and so on and so forth for all the other user and movie combinations. Okay, great. So now that we have the data set and we've visualized it, we understand what it looks like, what data we're dealing with. Now let's get into the implementation of the collaborative filtering. So we're going to be using the surprise package, as I mentioned. And the first thing we're going to want to do is we're going to create a reader object, and we're going to specify the rating scale. So we use, and I think you're able to do non-explicit ratings as well. But in this case, when you have explicit ratings, you just want to define what your rating scale is. So in this case, the values in our data set range from 1 to 5. So I've just specified this. And then here we're just creating our data frame from the dataset module in the surprise package. It's important to note that, again, if you want to use this notebook but change the data that it's using, you're going to have to need, as a minimum, the user ID, the ID of whatever the product you're trying to recommend, and then you're going to need a rating for it. So, and you also need to order it in this fashion. And I'm taking these columns from our ratings data set. And then the other parameter is just our reader that we just created. And so, okay, yeah, so this is where the magic actually happens. This is where the learning happens. And amazingly, Surprise, the module makes it as easy as just 5 lines. So pretty impressive. Right here, we're specifying our algorithm. In this case, we're using SVD, which stands for singular value decomposition. It's an algorithm which basically just makes solving our system of linear equations for the linear regression much easier. Like, it solves it for us. It does the cost calculations that we then need to use to then apply gradient descent when we're actually changing our model. So yeah, that's what we're using for calculating our mean squared error, or whatever our cost function is. Right here, we're creating our training set, and we just build that from the newly created data object in the cell before. And then we're fitting using the SVD algorithm. So we just do algo.fit and then train set. If you guys are new to machine learning, you'll often hear the term fit or train. These are just synonyms, they're interchangeable, and they basically just refer to the process of updating the parameters to optimize the cost function. So right here is where the actual learning of the feature vectors happen. Since we're doing collaborative based, we know the user vectors and we're trying to learn the feature vectors. So that magic is happening right in this line right here. The following line, we're creating the test set object, and we do that using Surprise's build anti-test set method, which basically just creates a good test set that it creates a test set from the training set that tests basically a whole bunch of different aspects of your data. And then we create predictions using the testing method from Surprise. And we do that with the algo object, which is now our trained model. So we make predictions on our testing set. So now, if we actually look at our predictions, you may recall that that user one, if we just go back up to our table of ratings, or this table actually, which just revisualizes it, we can see that user one rated movie one, but they didn't rate movie two. So if we just go up to our movies data set, let's look at what movie ID 1 and movie ID 2 is. So our user 1 rated Toy Story a 4, and they haven't rated Jumanji. And if we look at the genres, we see that Toy Story is not adventure, it's animation, it's children, comedy, fantasy. And if we look at Jumanji, it's adventure, children, and fantasy. And if any of you have seen Toy Story or Jumanji, you can probably affirm that these genres are relatively accurate. But we can also maybe guess that users who like Toy Story end up also liking Jumanji. So that's obviously a huge simplification, but just for our purposes of seeing like an example result from our predictions, let's predict just from our own knowledge that if user 1 liked Toy Story, they probably liked Jumanji somewhat, we'll say. So when we're testing it here, if we look at so user 1, we're getting our prediction for user 1, and we're looking at movie ID 2, and we're basically going through the prediction, all the predictions, and we're wanting to see what is the prediction that our recommender system gives for user 1 on movie 2. So if we go, I just realized that this is slightly wrong. I think this is supposed to be a 1 because that affects, because it should be, okay, wait. It's supposed to be our prediction for, I think just the way I'm printing it, I'll change that actually right after this, but I think the way I'm printing is slightly wrong. But I guess actually, hold on, we can verify it quickly that it's working as expected. I think it's just I'm printing slightly wrong. So we know that user 1 has rated movie 1. That means that if I change the movie ID to 1, we shouldn't get an answer. Yeah, so we don't get a prediction because there was already a prediction for that. So that's good. Similarly, we know that user 1 already rated movie 3. So if we give this movie 3, we shouldn't get a prediction. Great. Yeah. So but since user 1 hasn't rated movie 2, we should get a prediction as we did before. I think so. Yeah, for some reason I'm printing Toy Story when this should be Jumanji, and I think that just has to do with like how I'm printing out the name of the title, which happens right here. But okay, wait, what am I supposed to? I'll fix this after, but I hope that I've given you enough confidence to show that from the examples I've given that rating I am printing out is actually the prediction for Jumanji, and fortunately, it is the recommendation predicts that user 1 will give a 4.29 or 4.3 for watching Jumanji. Obviously, users can't actually give decimal ratings other than 0.5. So this is just like when we round it, we would predict that user 1 would actually give that Jumanji a 4.5, for example, which is a pretty high a high prediction for that movie. So basically, how we create our list of recommendations is we just sort by our predictions. Which one do we predict a particular user will give the highest rating, and then that's actually how we come up with like our rankings essentially for showing this movie I first versus movie I plus 1 is dependent on which has the higher predicted rating. Okay, cool. So the last thing we're going to do is we're going to assess the accuracy of our recommender system using what's called cross-validation. This is a technique in machine learning, which basically partitions your data set into a number of groups. In this case, I specified 5 groups. So basically, we partition our data set or our test set into 5 groups, and then we test it. We test our algorithm on each group separately and find what the accuracy, what the success of each section is. So in this case, we're using root mean squared error. Yeah, so that's our cost function for how for our predictions. And so in the first fold, we saw that fold is just another term for partition or group. So in the first fold, we see that it has a root mean squared error of 0.87 and so on and so forth. And across all 5 splits, we have a mean error of 0.8734, which means that our predictions will likely be off by around, our predictions will be off by the square root of that. I actually made an error of that. So it's even smaller. Our error is even smaller than 0.87 because we're doing root mean squared error. So our actual, if we, when I go back to the slides, I'll refer to what I was talking about. But if you recall, our cost function, we were taking the predicted value minus the actual value and squaring that. So the actual value that we're off by is when we do the predicted value minus the real value. So if we take the square root of this, that's actually how far off our predictions are to real ratings across our entire data set. So that means if our recommender predicts a rating if our recommender system predicts that a user will give a movie a rating of 3, the user will actually most likely be in the 2.5 to 3.5 range, actually. I have it as 4, but I'm going to just make a note of that here. Or I'll do that after, actually. But our range is actually going to be even smaller, which is good. It shows how easy this shows how easy it was to implement a collaborative based recommender system, and it does a pretty darn good job since our rating predictions are within 0.5 of the actual. So yeah, so now I'm gonna just show kind of like the biggest or a big first step in creating a content-based filtering recommender system, and that is actually creating the feature vectors. So so remember that in content-based filtering, you need product attributes, and those are what actually give you the feature vectors. However, they're not always formatted immediately. Like if we go back to our movies data set, we'll see that we have the genres: adventure, animation, children, comedy, fantasy, but they're not actually encoded yet. So encoding meaning that we just put a 1 basically in our feature vector for Toy Story, where corresponding to each genre. So if we go back here, I won't go into depth about like each line of this just because it's I'm just doing processing here basically. But what I'm doing from a higher level is I'm removing the pipes, and then I'm encoding each genre to correspond to the feature vector of each movie, and I put that into a data set called movie, or a data frame called movie underscore profile. And if we look at this, we can see that we have the movie IDs on the left, and a 1 in a row signifies that that movie is in the genre that corresponding to the 1. So just to verify this, we have movie 1, and we see that it's a children movie, it's animation, adventure, comedy, and fantasy. And if we scroll up, as you might remember, that's Toy Story, and that is all 5 of these genres that it's in. So what you would do after this is that you would basically use sklearn to apply linear regression on these. Again, this very similar to collaborative, but in the opposite direction. So this time we have the feature vectors, and we're trying to learn the user or parameter vectors. And so how you would do that is you could use one of scikit-learn's linear regression modules and basically fit using that. But it is a little bit more complicated because one thing that we have to remember with content-based filtering is that we're assuming that we have all of the feature vectors. However, in reality, you might not. For example, the recommendations that we would get using content-based may not be that good because we're only looking at genres, when in reality, there's a whole bunch of other factors that come into play when we're talking about a movie, such as the cast or the director. And all those things can influence whether someone liked the movie or not. So just basing it on genre might not be it might not be good enough in terms of the recommendations. But I would recommend looking into it. And I actually might add this to this notebook. And so if you just keep a copy of the link in the chat, you can maybe check back in like a week or so, and I might add that part of the code. It will be a lot more less straightforward and succinct as the surprise library did it, just because that's a much more popular, in comparison, it's a lot more popular to, if you're just to use one, it's a lot more popular to use collaborative based, just because that data is much more readily available than product data. And it's harder to encode product, or it's harder to encode product attribute data and actually learn from it that way. But it is a method that's used, and in tandem, it actually does improve the overall recommendations. So that's using the hybrid method that I was talking about before. But yeah, that's the end of the notebook. I just have one last slide. It's about deep learning recommender systems. I'm not going to really talk about this at all because this could be like another probably 30 minutes talking about it, especially if you're not aware of what neural networks are. But basically, just so that you're aware and you can look into it more at your own leisure. Basically, I've already shown the two most traditional recommender systems, and I've shown you how to implement them. But I wanted to mention that deep learning recommender systems is another approach that is used. Deep learning just refers to machine learning techniques which use neural networks. If you don't know what a neural network is, it's another type of machine learning technique, and we actually did a workshop in a previous term. So you can go to this link. I'll actually just, if you have the slides, I guess I think you should be able to press on that link and watch it on your own time. And basically, the deep learning recommender systems aim to understand this. Sorry, that was supposed to say the same relationships we discussed. So it's still trying to understand the user to user, user to product, product to product relationships, and it's also it's trying to learn the feature vector inside the neural networks. So it's really is the same concepts. It's just that the actual learning process is different. So so understand if you wanted to implement a deep learning recommender system, understanding all of the stuff I just talked about would still be very necessary in order to understand like the inner workings of the network and what is going on in the neural network. So if you want to, if you're familiar with neural networks and you want to implement a neural network based recommender system, TensorFlow has a good library. TensorFlow is just a Python module that's very popular for using neural networks, and it's very popular in the data science and machine learning space. But yeah, that's the end of the slides. Here are the resources that I use to kind of learn about this. This was just a article that I was reading about, and then I'd highly recommend, if you haven't already done Andrew Ng's machine learning course, I'd highly recommend you do it. It's a fantastic resource that gets brought up a ton when you talk to people in industry or at conferences, and it does a really good job of going over the math components that I was talking about. I actually borrowed some of his notation because it's a great way of describing data sets, and it makes the math a lot clearer. And it's okay if you haven't taken advanced calculus or linear algebra, because he does a great job of simplifying a lot of that. Like he basically gives you a crash course on what linear algebra does and what like multivariable calculus is doing. So yeah, highly recommend checking that out. This is another article that I referenced a bit in creating these slides. And then lastly, here's the UWaterloo Data Science channel. So it has a whole bunch of workshops that we've done in the past. So if you haven't been to them before, I'd recommend checking them out. So that's the end of my workshop. I was kind of in the groove, so I kind of forgot to ask if anyone has any questions. I know that was a lot of content. So if you wrote down a question and there was a particular slide that you were curious about learning more about, or there was something that was unclear to you, I'd be happy to answer your questions. I'm also in the Discord channel. My nickname should be Jack. I just have like a baseball player as my icon. So if you want to message me directly afterwards, if you for your own particular side project, or just have general questions for me, I'd be happy to answer them now or after. So thank you all for coming. I'll be taking questions now if anyone has any.